Hello everyone. In this lecture we want to go through again confidence intervals, but this time with an unknown variability, with unknown sigma. The learning objectives are to calculate a confidence interval for the mean of a normally distributed population, but this time with unknown standard deviation, and to understand why this added uncertainty increases the size of the confidence interval. Now, I'm going to spend one slide going through the idea of confidence intervals again. If you'd like to skip this, go ahead. This is a slightly different way of showing it. We've been saying that if we have a random variable x, which is distributed, doesn't have to be normally distributed, but distributed with a mean and a variance, and we take a sample of size n and calculate the sample average, then this will be normally distributed with the mean, same mean, and the variance over n. Now, let's draw this out here. I'll try and draw this carefully. I said you can skip ahead if you like. Okay, here we have our, this is a sketch here of the sample average. So we have here standard deviation over n, the known standard deviation over n. I try to draw this as accurately as I can. So I can draw out here then the number of standard deviations, and of course we've done a lot of this now. We can translate this into our z value. Our z values. Now, if we want to establish a confidence interval, if we know that we have a population, whatever we're measuring in our production, for example, we know the standard deviation is sigma, and we want to be able to take samples and then say with a certain confidence level where our mean of our overall population lies based on the samples. We choose a level. For example, we say 1 minus alpha is 95%. That means it gives us an alpha equal to 5%. Well, how do we come up with this confidence interval? What is the interval? Well, we know that very close to 2 standard deviations from the mean. It's actually 1.96 and minus 1.96, but very, very close to 2. If we shade this in, we have 95%, about 95% probability of falling within plus or minus 2 standard deviations from the mean, and a 5% chance of falling outside, or 2.5% on either side. So this gives us, and I'm going to change the color here, this gives us then an interval plus or minus about 2 sigma. Sigma is known. In this case, excuse me, plus or minus 2. In this case, it's sigma over the square root of n, because we're looking again at the sample average. A fixed interval, which we can then use whenever we come in. So say we come in on Monday, and on Monday we measure a sample average of size n for Monday. Well, we can construct about that value an interval. Actually, maybe I will change my color. Hang on. To make this look the same. So we'll construct an interval then of exactly the same length. These green lines should be the same. We say on Monday, this interval around my Monday value, my Monday sample mean, has a 95% chance of containing the true mean. And in this case, it does. It contains a true mean. Well, Tuesday comes along, and on Tuesday, we measure a a new X bar for Tuesday, sample size also size n, and same sample size, and we construct on Tuesday a confidence interval around the Tuesday value. We say we're 95% confident that our true population mean lies within this interval, and it does. And we do that every day, and we know that there will be one day, there will be some day, normally it would be the 1 out of 20 days, 20th day, for example, still sample size of n, where we construct our confidence interval here. Well, maybe we draw this a little bit lower. We draw this down here, bonk, 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 bonk. And on this day, we say again, we're 95% confident that our true mean lies within this interval. These intervals are all the same length. They're fixed by our original population. And here, no, it doesn't. So we're only 95% confident. 1 day out of 20, we expect that we won't have it. So that's the idea of the confidence intervals. And then we did the example. So we have the example here where we had turbidity measurements. So we had n equals 4. And we wanted a 99% confidence interval for that, the mean turbidity of the population of bottles filled on the line. And we knew we had a standard deviation of 3. Well, so we started with this 99%, and we looked in our table, and we said that means we need 0.5% or 0.005 on either side of our z distribution. That would give us, and z is, here we are lying exactly between these two values. So we have for 5%, that would be here 0.9950 on the positive side and 0.005 on the negative side. So z is going to be equal to 2.575, right between 0.7 and 0.07 and 0.08. And then we take our equation that we had here that the x bar is equal to 13, sigma we knew, 0.3. So we apply our equation, that was x bar minus the z alpha over 2 value times sigma over the square root of n, and the same thing plus, giving us 12.61 and 13.39. So that day, that Monday, we say we get a 13.0 value for turbidity, ppm, and we say we're 99% confident that we lie between 12.61 and 13.39 ppm for turbidity. So now we want to keep this in mind. Don't forget this, because we're going to compare this now. This is number one. Now we're going to look for what we do for confidence interval when the sigma is not known. So we have to go back a little bit into history to talk about William Gossett, an Irishman who was employed by the Guinness Brewery in the early 1900s, and he was using lab testing to help him find the best yielding varieties of barley to make their ale. And he needed to have correct methods for dealing with small samples. And so Mr. Gossett discovered the so-called student's tea distribution. He had to use a pseudonym because he needed to hide his identity so the competitors wouldn't get any ideas. And this T distribution, then, is a family of continuous probability distributions which are used for estimating the mean of a normally distributed population in situations where the sample size is small and the standard deviation is unknown. And this, of course, is much more common than when the standard deviation is often not known, especially if things are changing. And it looks like this. Instead of our z variable, we've got a t variable, where we have x bar is the average of our random sample of size n from a population with mean mu. And we have here the sample standard deviation. Now, we've learned how to calculate that in the first course. You take your your distance, every value in your sample, the distance from the mean, and square it and divide by the square root of n minus 1. So we had that before. And then we have the square root of n because we need to also, we're dealing here with this is x bar. So we're dealing here with a sample average. So this central limit theorem still applies. Now, this t value, this t variable, follows a probability distribution called the t distribution with n minus 1 degrees of freedom. Now, what does this look like? So I'm going to try and draw, this is the artist's rendition of the t distribution. Please look this up for a more exact picture yourselves, but if I draw a z distribution, our friendly old z distribution. This is a probability density function centered around 0. We have a certain standard deviation, which is equal to 1. Now, the t distribution looks slightly different. So, t distribution will be, again, this is be a little bit lenient with my drawing skills here. T distribution will be fatter, shorter and fatter, with thicker tails compared to the z distribution. And this, for example, is a t with degrees of freedom equal to 5. Now, what does this mean? So we have to go back a little bit to our probability. If we have, for example, the probability that our random variable x is between 2 points, we learned that we have to integrate our probability density function to get that probability. So if I take 2 points, for example, point A and point B, I have to integrate under that curve. And hopefully you can see here, the area under the z curve is going to be larger. The probability that z falls between A and B is going to be a higher probability than the probability that t falls between A and B. Why is this? Well, there's more in the t distribution, there's more of the probability is still lying outside these values because of the thicker tails. It's less certain, it's less exact than the z distribution. And why? Well, it's because the sigma is unknown. Here, the thicker tails are representing the uncertainty that comes from the fact that we have to estimate sigma using S when we don't know the standard deviation. Now, the reason the t distribution has this degrees of freedom is because as you increase your sample size, you get a more exact value. So for example, again, please be patient with my drawing. Here we have t equals t with degrees of freedom 25. As n goes up, doesn't have to even go up that much, that's far, you see that the t distribution starts to become thinner with lower tails. You're gaining some precision here with your distribution, of course, at the expense of doing more measurements. And so, as the as the n gets bigger, you start to approach your z distribution. So let's look at this as another picture of it. How do we use this? Well, we want to create a confidence interval for mu when sigma is not known, and we need to use then the statistic t. And what we need to find then, we go and look at the equation, it's exactly the same equation. So there's no need to worry about learning anything new. We have the x bar value. We have, instead of a z alpha over 2, a t alpha over 2. We have the sample standard deviation that we calculate instead of sigma and the same old square root of n, and we still have plus and minus the way we did before. So the new thing here, other than calculating S, is that we have to look in the T table. So don't be worried, you've done a lot of looking things up in Z tables, and I know in practice you'll be using, you'll anyway be using statistical packages or computers to calculate the T alpha over 2 and the Z alpha over 2 values, but we want to show you here how the table works. For the problems, we'll be giving you the values. So here you see the way a typical T distribution table looks like. And what we have here is this area is that alpha over 2 value. And when you make a confidence interval, you're looking for the point at which you have alpha over 2 on one side and alpha over 2 on the other. And this is just showing the one side. So, for example, if we want a confidence interval of 1 minus alpha equals 99%, or 0.99, this means alpha is going to be 1%. It's equal to 0.01. Alpha over 2 is going to be equal to 0.5% or 0.005. And let's say we have a sample size of 4, which means our degrees of freedom is equal to 3. So we look on our table for the degrees of freedom equal to 3. We look on our table for the alpha over 2, the shaded area, equal to 0.005. And if you go to the intersection, you see that the T for 0.005 with degrees of freedom equal to 3 is equal to 5.841. So again, with these tables, they always look very number heavy. We'll be giving you this value, but we need to see where this comes from, and now we're going to look at the example and do a comparison. So again, the confidence interval for the situation when we have an unknown sigma, the T alpha over 2 value, here it is again. If you have the same 4 turbidity measurements, remember that was x bar was equal to 13.0, n is equal to 4. Sigma this time is not known. How do we come up with a 99% confidence interval? So, n minus 1 degrees of freedom is going to be equal to 3. The T we just looked up for a 99% confidence interval with degrees of freedom 3 is equal to 5.841. And now this time we have to calculate S. S is calculated here as 0.365 from these values. 99% confidence interval, then using this equation, x bar was 13. Our T alpha over 2 value was 5.841. The sample standard deviation we calculated, and we have n the square root of 4. If you work that out, you get 11.93 and 14.06. We are 99% confident that the population mean for the turbidity on this day in parts per million lies between 11.93 and 14.06. Well, how did that compare to the situation when sigma known? And in this case, if you remember, it was 12.61 and 13.39. Which one is bigger? Which confidence interval is bigger? The confidence interval is larger when sigma is unknown. And does that make sense? We come in, we know the sigma. Let me take away this sigma known, point. In the case where the sigma is known, we can be more exact. We can be more exact, and we have a tighter limit for the same. Again, we're using the same 99%. We can tell our customer with more precision where we think the population mean will lie, or I'd be 99% sure that it will lie within 12.61 and 13.39. But if we don't know sigma, we can still tell our customer that we're pretty sure that it lies between 11.93 and 14.06, but that interval is larger. And this reflects then the uncertainty that is brought in from our t-distribution, and it reflects then here we also have the effect that the sample standard deviation was actually larger than, in this case, we had sigma equals 0.3. But you find that the t value is larger than our z value. Before it was 2.575. This was the z alpha over 2. And this t value is giving us that extra uncertainty and then incorporates that into our calculation. So why do we do this? Well, it's often necessary because the population standard deviation is not known. And then we're going to need to use a t-distribution to find the limits for the confidence interval. And the main takeaway here is the confidence interval will be less precise.